Hey there. Well, induction is a subject in mathematics that can arise in any number of places. So even though I'm recording this presentation as I'm recording my complex analysis class, this presentation probably can be watched in calculus as well as also in some other classes in which induction needs a quick review. And so that's what this is going to be. Let's just get to it. Let's talk about what induction is and then look at some examples as to where and how induction can occur. So let's see, what do we have? The principle of induction allows us to prove statements that hold for all natural numbers, and that at first seems a little bit complicated because if a statement holds for all natural numbers, that means it holds for infinitely many numbers, and that means we can't just check it at every single number anymore. So technically this is actually a set of infinitely many statements, one for every natural number, and that's what makes it sometimes so hard to prove. And of course we want to do this in finitely many steps, because checking every number we would never get done. So the trick there is to first prove the statement for one number, that'll be our starting point, and then to show that whenever the statement is true for a number, then the statement must also be true for the next number. Because what that gives us is that if the statement holds for the number 1, then it must hold for the next number, so it must hold for 2. Now that it holds for 2, it must hold for the next number, so it must hold for 3. Now that it holds for 3, it must hold for the next number, so it holds for 4, and it just keeps on going like that and never stops. And so as long as we can complete these two steps, then the principle of induction itself says it works for everything, and that's what we want. So it holds for all natural numbers. The principle of induction actually has the status of an axiom. Yes, it can be proved from some deeper lying axioms, but we're not going to go into. So even though it feels quite obvious and quite natural, it is something that we just have to accept. And the principle of induction states that if P of n is a statement about the natural number n, and P of 1 is true, and if for all natural numbers n, the truth of P of n implies the truth of P of n plus 1, well then P of n must hold for all natural numbers. Proving that the statement is true for 1 or for a starting number, that's also called the base step of the induction. And the proof that the truth for n implies the truth for n plus 1, that is also called the induction step. And so proofs by induction have a very schematic form. You always have a base step, you always have an induction step, and they're always quite similar. That doesn't mean proofs by induction are trivial, but there is something to start with at least. It's not like you have something and it says, well, go ahead and prove it, use anything you want. So let's take a look at some examples. Standard examples for induction proofs are summation formulas. So I'm claiming that for every natural number n, we have that 1 plus 2 plus 3 plus and so on plus n is n times n plus 1 over 2, a very well-known formula. Well, the base step, n equals 1, is very simple. You just plug in 1, and if you start a sum with 1 and go up to 1, well, that means you only have 1 on the left. And if you plug 1 in on the right, you get 1 times 1 plus 1 over 2, which is equal to 1. And so that means that the base step is okay. For the induction step, so assuming that the formula holds for n, we need to prove it holds for n plus 1. We look at the sum from 1 through n and then n plus 1, and we realize that this start up here, and the highlighting isn't as pretty as it could be with the way I'm generating the slides, but this sum up here, that's just this sum over there. So this is just n times n plus 1 over 2 plus n plus 1. And if I now find a common denominator, that's n times n plus 1 plus 2 times n plus 1, which is n plus 1 factored out times n plus 2, and n plus 2 is n plus 1 plus 1. And that's, of course, what we wanted to show. We wanted to show that this formula with n replaced by n plus 1 is true also, and that's what this part does here. Okay, now the interesting thing about induction is that induction doesn't just work for stuff that you can write down as a formula. It also works for things like geometric statements, such as the example here, which says that the sum of the interior angles of a plane n-gon with n greater or equal than 3 vertices is n minus 2 times pi. So this is the generalization of a result that you know from geometry, which is that the sum of the interior angles of a triangle is equal to pi. Basically what this now says is every time you add a corner, your sum of interior angles increases by pi. Well, the base step would be n equals 3 this time, because we only want the result for n greater or equal than 3. And if we look at that, well, that case is this well-known result for triangles that I've mentioned. I can prove that too, but the focus of this presentation is on induction itself, and so I'd rather refer you to the literature or to your knowledge from high school for that. And now let's take a look at the induction step. Well, the induction step here has a very simple idea. You get an n plus 1 gon by tacking a corner onto an n gon, right? So if we cut a corner off an n plus 1 gon, if I cut a corner off of a, say, a square, well, if we do that, we don't get something with 5 corners, because that would mean we've actually added something. I always want to cut corners in such a way that I go from one vertex to another. So if I cut a corner off of an n plus 1 gon, I get an n gon. And if we're, so that means we're done if cutting a corner off an n plus 1 gon reduces the sum of the interior angles by pi. Well, let's see. First of all, we'd have to find the right corners. So an n plus 1 gon is just something that can be highly irregular and can do whatever it wants out here. And here's one corner. And what I mean by cutting off a corner would mean to really go from this vertex to this vertex. So here are vertices ak minus 1, ak, and ak plus 1. And if I now just put a connection from here to here and throw this part away, I've cut off a corner. The only thing that could go wrong is that this might somehow make the n plus 1 gon self-intersect if this thing is just highly irregular and seriously concave here. But if that happens, I would just work with this corner instead. And if that corner has a problem, I just keep going. I will ultimately find a corner that looks like this. And if this is a convex corner, meaning that this is actually interior to the n plus 1 gon, well, then I know this is the angle alpha k plus 1, alpha k, and alpha k plus 1. And the sum of these angles is pi. And that's exactly what's missing if I cut that corner off right here. So that means this n gon here has a sum of interior angles n minus 2 times pi, and then if I go from that n gon to the n plus 1 gon by putting that corner back on, I add pi to it, so I get n plus 1 minus 2 times pi as the sum of interior angles. And it could also happen that I've got a concave corner, which is what happens if this corner that I found goes this way into the n plus 1 gon. Well, I do the same cut. I have the angles now, this time sitting here and here. These are the interior angles. I still want to call these things alpha k plus 1, alpha k minus 1, alpha k, and alpha k plus 1. And now I realize, well, okay, this time around, this interior angle, if I make the cut here, is actually increased by alpha k minus 1, and this angle here is increased by alpha k plus 2. And the sum of those is pi minus alpha k. So I've actually gained something here, but remember, I've lost this angle, and this angle is 2 pi minus alpha k. Well, if I lose 2 pi minus alpha k and gain pi minus alpha k, I've totally lost pi, and that means, again, going from the n plus 1 gon to the n gon, I lose an angle of pi, which means the result is proved. The principle of induction has a variety of forms, and that's what we're going to conclude with. For example, every non-empty subset A of the natural numbers has a smallest element. Sometimes we use that in order to prove something by induction, but here we're just going to prove this statement itself. So proof, well, if the empty set is not equal to A, and that thing is contained in the natural numbers, then we suppose for a contradiction that A does not have a smallest element. Well, we let the statement be that the intersection of the beginning of the natural numbers from 1 to n intersect A is empty. And we will prove that that works for all natural numbers, which would then of course be a contradiction because it would mean that A doesn't intersect any beginning of the natural numbers, and that means A would have to be empty. For n equals 1, we realize that 1 is the smallest element of the natural numbers, so that means that 1 is not an A, and that means P of 1 is true because singleton 1 intersect A must be empty. Going from n to n plus 1, we assume that the intersection of 1 through n intersect A is empty. And we consider the element n plus 1. Well, n plus 1 is the smallest element of the natural numbers minus 1 through n. And that means that n plus 1 can't be an A because none of these guys is an A, and that means n plus 1 would be the smallest element of A. And that means P of n plus 1 is true because now 1 through n plus 1 intersect A must be empty because n plus 1 is not an A. So that means P of n holds for all n element n, which means that no number n is in A, and that means A is empty, which is a contradiction to our assumption that A is not empty. Okay, so that means, because we have arrived at a contradiction, A must have a smallest element, because that's what the assumption was that we wanted to lead to a contradiction, and we have. And that would be the principle of induction in its smallest element form, if you will. Induction also is sometimes formulated as what some people call strong induction. If you need a really strong hypothesis for your induction step, you do the following. You let P of n be a statement about the natural number n. If P of 1 is true, and if for all n element n the truth of P of 1 and P of 2 and P of 3 all the way through P of n implies the truth of P of n plus 1, then P of n holds for all natural numbers. So this wedge here is the logic symbol for and. So this means P of 1 is true, and P of 2 is true, and so on all the way through P of n is true. The proof reduces this to regular induction. I let Q of n be the statement P of 1 and P of 2 and so on, and P of n. And I will prove that that Q of n holds for all natural numbers, which then of course automatically means that P of n must also hold, because P of n and some other stuff can only hold if P of n is true. The base step, well, by assumption Q of 1 is true because it's equal to P of 1. And the induction step is that we let Q of n be true. Then that means, because Q of n is P of 1 and all the way through P of n, that is true too. And by assumption, that means that P of n plus 1 is true. Okay. But that means that Q of n plus 1, which is P of 1 through P of n and P of n plus 1, we know now that that is true. And that means Q of n holds for all n by principle of induction. And that means P of n holds for all n. And we are done. Okay, that was a quick run through the principle of induction. Certainly very wide-ranging. We've talked about sets, we've talked about logical formulas, we've talked about geometry, and we've talked about a summation formula. Most likely in your initial exposure to induction, you will talk a lot about summation formulas and various kinds of formulas. So the first example ought to be the one that guides you the most in the near future. The one thing that can and does change is that the algebra gets a little bit harder, but the basic setup, which we've also seen here over and over again, this 1-2 punch, base step, induction step, that always stays the same for induction. So, well, get back to what you're supposed to do with induction, and I hope this has helped. Thanks.